this. Now, give me a sketch. Right now, we're on your standard normal curve. We're putting your standard deviation at your mean at 0, your standard deviation at 1. We're looking for your z-score. So where would I find the z-score of negative 1.54? Between which two? Negative 1 and negative 2. And I want my area to the left. Now, you look up your negative 1.54 on your table, and that's the z-score, that's the area that corresponds to the left of this number. So what would you come up with? 0.0618? Okay, that's the area to the left of that z-score. Now, the second one is give me the area to the right. Between which two values do I locate 1.54? 1 and 2, and you want the area to the right. What's that answer? Same thing. Okay? Does everybody notice that it's the same thing? Or you could use the rule that this total adds up to 1. You could look up the 1.54 and then subtract it from 1. Because we want the area to the right. So if you looked up the area for 1.54, what area did you get? 9,382. Thank you. And do you notice that when we subtract it from 1, that's your answer? Could it have been 93%? It's not more than 50% of your curve. This is why your sketches are useful. Because I want to see it's not 50% of my curve. It's a little tiny piece. This piece and this piece, we're using the property of symmetry for your curve. It's the same distance away from 0. It's kind of almost like an absolute value concept, that the distance is the same from 0. So your curve is symmetric about the mean, where the 0 is located. So this area is the same as this area. Then we had to do an in-between. You had to do an in-between. And I'm just going to put my positives out here. An in-between 1.12 and 2.24. And if you had to guess before you did this, if you had to estimate, what could you estimate this as? Off the top of your head, I realize you did the problem, but what would you estimate it to? How much percent? Right in between here. 12%, 15%, 10%, somewhere smaller like that, right? I'm only looking for an in-between. And it's a little past my 1, so I kind of started to go down the curve a little bit. And past my 2 is unusual, so that's small. So maybe I would say 10, 15%, if I want to estimate. Now, that helps you, because when you look up your curve, I'm always losing my table. When you look up your curve, your 1.12, 0.888. Is that it? Nope. Sorry. This is why I always use my calculator. Can't follow the table. 0.128686. And when you look up your 2.24, thank you. You're going to subtract those areas. You're going to find a small amount of area because you're always going area to the left. You're taking out where they overlap, which is this whole big thing where they overlap. So what's your final answer? Point what? 1? Thank you. So therefore, 12%, 12, 15, 10%. If you estimate it in there somewhere, at least you know you're on target. Now, yesterday we also took a look at your calculator to do this. The in-betweens work the best.
If we were to do this on like a test or something, and we just like, do you want us to leave it in decimal or do you want us to put it into a percent?
Well, if you're just finding your area, the percent doesn't really matter yet. Today we're going to actually change them to percents because today it relates better to a percent. But if I'm just asking you to find your area, you can leave it like that. Now, in your calculator, when you look this up and you go to your normal, remember, it's your lower limit, your upper limit, your 0, your 1. We're on a standard normal curve. Your lower limit is the 1.12 z-score. You could see that's the left limit, the lower. Your upper limit was the 2.24. Your mean is 0. Your standard deviation, 1. The in-betweens work the best because that lower and the upper limit you actually can see. If you're on the left one, you got a negative 999. The right one, you got a positive 999. Sometimes kids have a harder time with that. But the in-betweens work really nicely. So good? Okay. I do want you to get used to looking up your table. And when we do today's, I want you to get used to just, do your z-scores a couple of times. And then I'll show you on the calculator how you can even do the applications that we're doing. And then I don't care which one you use. But I just want you to give it an option up front to be able to use both. Okay. Now today, what we're going to do is, and I put this on your notes, we're going to incorporate the two tables into one. We looked at the properties. We used the fact that they're symmetric about the mean. We used the fact that they're equal to 1. We know your cumulative area is from left to right. We're going to incorporate these properties into one curve that we're going to use for the rest of this time. So I took these two curves. They're in your book. This is your standard normal curve. This is your normal curve. Your standard, your normal. They're the exact same curve. They have the exact same percentages on it. All they do is, on this one, look at the mean is 0. And your standard deviations are here. On this one, the mean was 500. They put all their x values here. I do mine a little bit differently, and I think you'll understand it a little bit better. So, pull over to the side here, and we're going to make one curve now. And we're going to incorporate both of these concepts into one. Your standard deviations go on the bottom. I'm looking for these kind of sketches. Put your standard deviations on the bottom, same as your standard curve. Put your x values across the top. So your mean is going to go in the middle. Put your standard deviation for that top curve. They didn't tell us. It's 100, right? It's 100 away, 100 away, 100 away. So that's what we did. We added 100 each time. And then we subtracted 100. Remember, we read left to right. So we subtracted 100. So we're going to make one curve that we're going to use. So now if I say what is the probability that x is greater than 600, I can look at this, see that it falls, where my standard deviation is, where my x value is. We're going to use one curve for this. Right? And by the way, they have to tell you that your data set is normally distributed. That's why you see that on everything that you do. If it's not normally distributed, we can't do any of this. We can't do this at all. We can't use your z-score formulas on this. So they usually say that your data, your random variable x is normally distributed. Follows this curve. All right, so let's take a look at an example. We're going to set up your probability statement. We're going to give it a sketch. We're going to convert to a z-score. We're going to find your area. All right, this is from your book, page 249 or something like that, 246. I'll read it. God bless you. Where is it? 246. Okay, a survey indicates that people keep their cell phones on an average of 1.5 years before buying a new one. The standard deviation for this scenario is 0.25 years. A cell owner is selected at random, we want to find, and this is what we're looking for, what we want to find, the probability that the user will keep his or her cell phone for less than a year before they buy a new one. You want to find what's the probability that they will not even wait a year. Okay, now start with your probability statement. This is what I'm looking for. The probability that X is what? Less than 1. That's my probability statement. I want to know what is the, that's why I'm doing this whole thing. What is the probability that this cell phone user got rid of their cell phone before the year was up even? Well, before it was less than 1 year. Now, we're going to make a sketch, just like we did before. We're going to start like this. We're going to pull out your mean. Always pull out your mean and your standard deviation. Pull out your mean and your standard deviation. Put that onto this curve at the top. There's your mean, 1.5. We're going to add your standard deviation, 0.25, so 1.75. Oops. We're going to add another 0.25, 2, another 0.25. We're going to subtract. Now, usually if you're greater than 1, wherever you see it, and if it's to the left or to the right, you don't have to do the whole thing, but this one I have to do because I have to go backwards anyway. 1.25, there's your 1, subtract another one, there's your 0.75. These are your X values that correspond to those standard z-scores. Now, you want the one that corresponds to the 1. Here's my 1. You want your area to the left. Yesterday we looked up z-scores with area to the left, area to the right, area in between. The only difference today is we're going to convert that X value to a z-score first. We're going to use your formula. I realize you can see the z-score, you can see the standard score on there, but this one just is unique that it happened. We're going to use your formula. And the sketch is helpful too, because if it's to the left of the 0, your z-score is negative. If it's to the right of your 0, your z-score is positive. And the reason I say that is, your formula says x minus the mean. I don't know what it is from when you're young, but kids subtract the larger minus the smaller, because it just seems to make more sense for them. And you come out with a positive z-score, but this sketch will help you say it's negative. So I have to subtract the smaller minus the larger. And I'm going to find my z-score. And I find my z-score. I look up in my table the area to the left, which is what my table says. So I look up in my table, and what area to the left do you find of negative 2? I subtracted the x minus the mean over the standard deviation, 0.25. This says negative 2. So look up negative 2, and what's the area under your curve for negative 2 to the left? Do I expect it to be a lot or a little? A little. So when you look it up on your table, what is it? 0.0228. Now, here's where we turn this to a percent. We say 2.2%, 2.28%. So the probability that this random user kept their phone for less than a year is about 2.28%. Is this unusual? Anything less than 5% is unusual. Anything at negative 2 to negative 3 is unusual. It's unusual that they wouldn't have even waited a year, according to this chart, according to our scenario here. Did you look it up in the table, -2? Look up -2.0 and come all the way out here to the 0.00. Remember, the negatives go the opposite way. When I first started teaching this, and I would always count in my head 0, 1, 2, 3, 4. It took me a long time to, doesn't long, you know, long enough to say, oh, the negatives go the opposite way. See it? Okay? Now, we're saying that the probability following this scenario, following that we have found over the years, the average is 1.5 and the standard deviation is 0.25. The probability that they keep their phone for less than a year is almost like a little bit more than 2%. 2% chance that they kept their phone and they got rid of it before their year was up. Okay? So what the sketch helps you do is, it helps you get a good grasp on how these x values correspond to your z-scores. And it still helps you figure out your area under the curve. Should it be greater than 50%, less than 50%? Am I supposed to subtract from 1? I should be able to tell. Like if my area is to the right, and I look up an 80-something% thing, well, I know I had to subtract it from 1. Questions on this? It's a lot to digest. We're combining everything together. Okay, now I want you to try it 1. I want the same thing. I want a probability statement. I want a sketch. I want your shading. And flip it to a percent so we can interpret it at the end. P.S. Let me just walk you through this one because it seemed to be a little bit of a discrepancy in the last class. Where average speed of vehicles traveling on a stretch of highway is 67 miles an hour with a standard deviation of 3.5 miles per hour. A vehicle is selected at random. What is the probability that it is violating the speed limit of 70 miles per hour? In other words, if you do 70 or more, you violated the speed limit, right? So that's the x part you're looking at, the 70. The mean is just the average on that road, not the speed limit. What is the probability that this person at random is going 70 or more? That's what it's asking you. It's a kind of a weird way to say, is it violating your speed limit? Violating means, are you going that faster than your speed limit? That's what it's trying to say. Faster than your speed limit. The average speed is less than the speed limit. We always assume that they're normally distributed, because if they're not, we can't approach this problem. Yep, make a sketch. Keep adding your 3.5. I want your sketch. Yes, start with your mean in the middle, add your 3.5 all the way up. And then subtract it the other way. I want you to get used to seeing your x values and your standard score on the same curve. Back here.
And what are you rounded to?
What, your z-score? To 2 decimals. If you're looking up in your table, you can only look up 2 decimal places. Yep, you have to round that to 2 decimal places because that's your z-score. Well, write the whole thing out and then just round it to your 2 decimals. When you look up in your z-score table, you only get 2 decimal places. So, of course, our rounding causes us not to be as exact. We're going to do this on the calculator later, and I'll even show you on the calculator how to do it. Put your x values in there. It's pretty neat. You can bypass this whole z-score thing, and but I want you to be able to see it with the sketch and with the z-scores. You're looking it up on your calculator, Rick? Special calculator. calculator? Yeah. Mhm. Yeah, but that's different. That's a different problem. That's your z-score right there. Round it to 2 decimal places.
So meaning violating the speed limit means going over 70 miles?
Yep. Yep. Exit the R70. That's going to be our cutoff point. So 70 and above violates your speed limit. 2 decimals, because that's your z-score. See how your z-score is only 2 decimals on the top here? You're going to look up your area. So from there, you're going to look up your area here. Yep. So no, this is not a 1 anymore. This is 67. Your speed limit is 67. And your x value is 70. That's our cutoff. 70 minus. Yep. You gotta find your area. Where's your shading? What part do you want shaded? Your x is 70. And we want anything, your probability statement is missing. Probability that x is greater than 70. Yeah? So now when you look up your area, you want the area to the right of that z-score. Guys, we're combining what you did yesterday, finding the area, with putting an x value there first, and getting that related z-score, and then doing exactly what you did yesterday. Look up the area for it. Since it's to the right. Because it can't possibly be that big, right? Alright, let's set this up. I know there's a couple of problems here. I've got an average speed, and I have a standard deviation. If you're going to go 70 miles an hour or more, you can get a ticket. You're going to violate the speed limit. That's what they mean by violating. So start with your probability statement. This is your x value. It can't be your mean because it gave us the mean and the standard deviation up here. So the probability that x is more than 70, God bless you. 70, more than 70, you could possibly get a ticket. You're going over your speed limit. Okay? Now, your graph is going to help you, your sketch. Start with your standard deviations on it. Then put your x values across the top. What's your mean? That starts up here, 67. Add 3.5. Add 3.5. Keep adding 3.5. And subtract 3.5. And you can go all the way down subtracting 3.5. So this is 63.5. Thank you. Now, we want to know the cutoff of 70. If this car is going 70 or more, they have the possibility of getting a ticket. They're violating the speed limit. 70 or more. Now, I want the area, just like you did yesterday. I want the area to the right of 70. So I have to find what's this z-score first. Then look in my table and find the area to the right of that z-score. So I use my z-score formula. My x value is what? 70. My mean is, and my standard deviation. So what's my z-score? 0.85 what? Okay, now, in my table, my z-scores only go 2 decimal positions. So round this to the 100th position. So I'm looking at a z-score of 0.86. Does it fall between 0 and 1 where I thought it would fall? Does it fall closer to the 1 like I thought it would? Now, you're going to look up in your table a z-score of 0.86. And when you get your z-score of 0.86, you're going to say 0.8501, right? 8.8051. you're going to say, could that be more than 50%? No, it's half. It's less than half of my 50%. So what do I have to do? Subtract it from 1. Look up in your table 0.86. There's your table 0.8. And here up here 0.06. See it? Probably you might be off at the decimal. And that's this area right here. Now, by looking at this, it can't be more than 50%, so we knew to subtract it. So 1949, is that it? Now, that's the area to the right of that number. What's another way I could have found that area? What else could I have looked up? The negative of that. I could look up the negative of 0.86. I could look up this side. That's the same area. I don't want to change my z-square formula. I just maybe want to look up the left-hand side of it and say, oh, that's 0.1949. Now, it makes more sense when you move this to a decimal. When you move your decimal to a percent. So I have a 19.49% chance that I choose a car at random that is violating the speed limit, going more than 70, as I'm scanning my stretch of road here. Okay?
You would accept it as either a decimal or a percent.
Well, I would accept it as a decimal, but if you have to interpret this, like saying 0.1949 doesn't really make any sense. Your probability, you should, in this case, flip to a percent, just so we could interpret what does this mean. That's the whole reason we did this, to find what is the probability that I will randomly select a driver who's going more than 70 miles an hour. Right? So I incorporate my x values onto my standard normal chart so that I could see how they relate, how the x value relates to the z-score. Good? All right. Now, I'm kind of running short on time, but instead of starting the next one, I'm going to give you a couple to try for homework. And you can start them now. These. I don't want to give you the in-between, so I'm going to give you the
We don't have to do one for each step.
no. Well, if you did it, then you're one step ahead because you did the in-between.
Yeah.
Wow. Okay, good. For all you guys that like the calculator, did you figure this out on the calculator? No? Okay. Did you write that down? Let me show you the calculator a second. I can do it over here. That last one that you did with the x value,
No, I was gonna go.
okay, watch how nice this works with your calculator. We used your, guys, we used your normal CVS. By putting in our z-scores and putting in a mean of 0 and a standard deviation of 1, we put our z-score in and found your area. Well, watch what we can do now. We know your x values. We want your lower limit, your upper limit. Well, here's my graph. Here's my 70. I want 70 and above. Guys, give me 1 minute. So my lower limit is 70. My upper limit, 999. Now, my mean is 67. My standard deviation is 3.5. There's my area under the curve. 0.1957. It's slightly different than the 1949 that you found. The only difference is in your rounding. When we found this, we rounded your z-score. We rounded this. Your calculator doesn't round. So your calculator can find your area based on an x value. But the only difference is, look, I have, instead of the 0 and the 1, I have to put in my mean and my standard deviation of my x values. If you do this, you bypass your whole z equals thing.
And you writing to the only one that's
Well, you're going to take your decimal and make it a percent. Because if I say, what's the probability that this driver is going 70 or more? If I say 0.1949, that doesn't really make sense. If I say it's a 19% probability that I'll pick a random person who's going more than 70, that makes more sense. So the calculator is really nice to do this with. But I do want you to get used to doing your z-scores and starting it there. Whoops. I guess I can take that back there. All right. But we did that one for homework. We did the one with the multiple choice, and it was a quarter or 3 places in the third.
Something's missing and you're not
That sucks.
With the text, yes, with the text back.